We'll get right into it. Here's our new paper, Dual System Transformers, Fast and Slow. I'm Rohit.
And I'm Ganesh.
So first we'll talk about the motivation for our idea in this paper. And that's essentially that language models are getting larger and larger, right? And we're sacrificing inference time or speed for the sake of performance. But in this paper, we try to investigate if we can have both speed and performance. So the way this is classically done is through idea called mixture of experts. And that's essentially by kind of referring to the idea that there is a layer or a gating network that will take inputs, right, in the middle of a transformer and route it to a certain set of experts. So in this example, we have n experts, and the gating network is going to choose two experts. So this is commonly called a sparse gating network, which is used for a mixture of experts. And so it'll choose two experts here to send the tokens to. And each expert is basically the feed forward layers of a transformer. But instead of just one transformer having one set of feed forward layers, they're going to have n different independent feed forward layers that are going to kind of try and specialize as the idea on different types of inputs. So in our case here, we're trying to optimize for speed. So we're thinking of having an expert that's very big, right? And that does very complicated tasks, even though it takes its time. And then we have an expert that's small, which can do very fast and smaller tasks. So this kind of brings us to another inspiration, which is the book Thinking Fast and Slow, where he talks about two different systems, right? Where system one is a fast and instinctive system, right? It solves problems like 2 + 2. Whereas system two is a slow and deliberate system, which solves a more difficult problem, say 17 times 24, right? And so these two systems are necessary, right? And you have to choose when to use which one so that you can optimize your accuracy and optimize your speed at the same time. So we apply this model in the ML, kind of a model of thinking in the ML world. So let's kind of get into our actual solution now. So we have two systems, right? Two LLMs for our language modeling problem, which is a large language model, which is very big, and then another language model that's somewhat smaller. So we'll call this L and S. And we also need to train a third transformer, right, that will act as a gating network. And this gating network is essentially going to classify the input sequence on the difference in the log probabilities of the large network and the small network. So what exactly does this mean? This means the gating network is in charge of selecting which LLM, right? Or if the larger one, how much better the larger one is than the smaller one on a given input. So we can sort of think about this as a threshold now. How can we set a threshold that will now then direct the input to a certain LLM, right? The large or the small one. So if g of x, right, predicts something that is higher than t, then it predicts that L is going to perform much better than S, right? And so it will be worth this extra accuracy, right, to use up some more time and send the input to L, the larger model, right? Whereas if it's less than t, right, it believes L isn't going to perform that much better than S. You might as well just send the input to the smaller model, right? So you could take advantage of the high inference time, like the low inference time, and speed up our overall runtime.
And now I'll go into our implementation of the dual system architecture. So as we mentioned before, there are three sort of neural network components that make up this whole scheme. First of all, there's a gating network, which determines which model actually sees the input. This needs to be an encoder-only network, and so we choose Distilbert since it's relatively small, but still performs well on these language tasks. For our fast and slow models, we use two sizes of GPT-2, which are 120 and 770 million parameters each. While this is much smaller than many models that are in use today, we believe that the results can be extrapolated to those larger sizes as well. So here's a diagram that shows sort of the flow of input through the dual system architecture. First of all, the gating network, in our case BERT, sees every single input and determines which of the two other models actually returns the result. So for easy problems, BERT decides to pass it to the small GPT shown above, and that output is returned. But for more difficult problems, it may choose to pass the input to the large GPT, whose output is then returned in the end. So in order to prove the concept of the dual system architecture, we run a series of experiments. Specifically, we use the tiny Shakespeare dataset, which consists of around 40,000 lines from various Shakespeare works. It consists of about 300,000 tokens as computed by the GPT-2 tokenizer. Throughout our experiments, there are a few variables that we keep track of. First of all, we have the threshold value t, which we vary across a wide range of values. And then there are several performance metrics that we measure as well. So first of all, there's average time per sequence. So we use a fixed context size of 16 and take the time that the overall model requires to run on each input. We also measure loss through the perplexity score. And finally, we look at top 1 and top 5 accuracy on the next token prediction task. So looking at the results of the experiments, on the left-hand side, we have a table that includes the results for various threshold values. On the right, we have a graph that shows the overall trends. So there are a couple of things that are important to note here. First of all, it's a decreasing function. So this is as would be expected. As we spend more time on a task, we perform better on it. So our perplexity loss is lower. And also we see sort of the law of diminishing returns, right? It's like a concave function, which means that as we spend more and more time, the marginal time that we spend is actually not as beneficial. So there could be some spot in the middle where we're making the most of the time that we spend and not spending unnecessary. Cool. Moving ahead, we have a couple of accuracy plots. So this is top 1 on the left and top 5 on the right. Once again, we see a similar trend where we have this overall increasing trend with sort of this diminishing return on the right-hand side of the graph. And I think this very clearly illustrates the power of this dual system architecture. We can see that we can reduce the time spent on the average input by from 45 to 30, which is a 33% decrease, without really decreasing the performance that much. The top 5 accuracy, for example, only goes down from 47 to 46, which is marginal considering the great decrease in time spent. There are several avenues that we'd like to explore in the future. First of all, we'd like to experiment with different pairs of small and large models, apart from the ones that we've tried. In addition, we could try fine-tuning the models themselves on the examples they see. So maybe the small model can get even better at those small tasks since it doesn't need to worry about the more difficult ones. In addition, we could experiment with having more than just 2 models. So this is sort of an arbitrary choice that proves the concept, but really we could have a small, medium, and large model, for example, that allows our gating network to make even more fine-grained decisions on how much time to take for each example. So that summarizes our work, dual system transformers, and thank you for listening. Nice.